I want to say welcome to you on behalf of NLM's Extramural Programs Division. I'm Valerie Florence, one of the lucky people who works there. And I want to welcome you to our Biomedical Informatics and Data Science lecture series. We do this 3 times a year. And this will be videocast live, but it'll also be archived and available on the NIH videocast. So I am really delighted to be introducing Samantha Kleinberg, who is our speaker today. She is an associate professor of computer science at Stevens Institute of Technology. She received her PhD in computer science from NYU, was a computing innovation fellow at Columbia in the Department of Biomedical Informatics, is a recipient of an NSF Career and JSMF Complex Systems Scholar Awards, 2 different awards, and is a Kavli Fellow on top of that. I probably said that wrong. I've always looked at it and said Kavli, maybe it's Kavli, if you recognize one of those 2 words. But a very prestigious fellowship. She received her first NIH research project grant from us, right, in Big Data, Causal Inference, and Large-Scale Time series with rare and latent events. She's the author of 2 books, Causality, Probability, and Time, and also Why, a guide to finding and using causes. I like that. She's published a number of articles on data science topics as well, ranging from replicating data-driven experiments in multiple systems and patient populations to combining Fourier and lagged k-nearest neighbor imputation for biomedical time series data. And we're fortunate also, she's a member of our study section right now, the Biomedical Informatics Library and Data Science Review Committee. So the title of her talk, as you know from the flyers, but I'll tell you again, is From Data to Decisions, Large-Scale Causal Inference in Biomedicine. She'll be speaking, and then there will be time for questions after she's through, unless she says, interrupt me at will, which I don't think she will, but you never know. Welcome, Samantha.
Thank you. You can interrupt me at will, unless there's like major interruptions, then I'll say maybe we'll save it for the end. Thanks so much for inviting me. I'm really excited to talk about the work I've done that's been mainly funded by NIH, which has been my largest and most consistent supporter of my research. So this is the sort of data science problem that I work on. This is a patient in the neurological ICU at Columbia, where I collaborate with the head of neuro ICU, Jan Claassen. This is what he sees when he goes in to treat a patient. He sees a person, many disconnected monitors. This happens to be an advanced ICU where this data is actually recorded into a database. That's not true of all ICUs. It's not true of actually any other ICU at Columbia aside from neuro ICU. And there, you're lucky if you happen to see a number that's useful. You have no idea what's happening in between those, or maybe someone writes something down that you can actually make sense of later. It's also a major human factors problem. Here, all the monitors are telling you different things, and it's up to you to maybe see a useful pattern that you can use to treat a patient. And so I think it's a super interesting problem. The challenge has been mostly computer scientists have looked at this and said, how do I figure out what's happening and create an alarm about it? So I can trigger an alert and tell the doctor what's happening. And then of course it's well known in biomedical informatics, alarm fatigue is a huge problem. Most of the alarms are not actionable. They tell you what's happening and it's not something you can do anything about at all. Even worse, people can't tell the difference between most of the alarms. And there are studies showing people can't distinguish between them at all if they make different sounds. And then, of course, it's a major safety concern because people start ignoring the alarms and then they don't pay attention to the ones that are actually important and actionable, right? And so what doctors really want to know is not what's happening, it's why it's happening and what can they do about it. So in this talk, it'll be primarily, Valerie said my book is called Why. How do we get to the answering why questions? So the first part is how do we go from data to knowledge and figuring out why things are happening? The second part of the talk, I'll get into what can we do about it, which turns out to be a very difficult question that requires other solutions. And so first, why should we care about understanding why things are happening? Why is causality a problem? Especially in a data science lecture series, often there's a question, do you really need to know why things are happening? If you can do classification or if you have okay accuracy for prediction, maybe it's not so important, right? And certainly with the rise of deep learning and other technologies, there are a lot of situations where we can do prediction and classification. We have absolutely no idea why they work or what's actually happening under the hood. For medicine, that's problematic, right? If we don't know why things are happening, I'll talk about a few cases. And I'd argue, even for prediction, even if you don't want to do intervention, you want cause relationships. And so if you're going to create any kind of action, you need causes. First example is, even if you just want to predict, this is the classic case where people would argue, who cares about causality? Causality is hard. We can do this with deep learning or other tools. But if you don't know why things are happening and why your prediction works, you can't understand when it's going to stop working. And a major example of that was Google flu. And so a few years ago, Google was using search keywords to predict cases of the flu. And they were able to do it with higher accuracy initially than the CDC could. And this was a super interesting tool, right, for epidemiologists. But then, of course, at some point, this stopped working, and then the articles in Science, and Nature, and other places all about the failure of Google flu, when at one point it started estimating cases of the flu that were double the CDC estimate. And of course, it's because there's nothing causal about searches and you having the flu. You could read about Google's flu trends and then start searching flu terms because you know that Google is doing this. Maybe you've heard about the flu on TV, your friend has the flu, right? There's not a one-to-one link between you're having the flu and making searches, and so you don't have a robust prediction. Even if you don't care about doing anything else with the information, you've now failed at prediction because you don't have causal relationships. And so that's the first thing we want to do with causes, is be able to say something about what's going to happen in the future. The second is explaining why things happen. So if I work with primarily time series data. There are lots of time series that look similar. This is a funny one. There's a website that crawls the web for time series and puts together crazy time series that have similar trends. There's another one, I think, with computer science doctorates and like video games and arcades. There are a lot with cheese for some reason. But this is, of course, they're just non-stationary time series, and any non-stationary time series that has a similar trend is going to seem to be very correlated. But here the correlation that's not shown is like 0.94 or something like that. If I put something else with that, then you could make a story about why these things are related, and there would be no reason for that other than, right, they're non-stationary time series. And so this is a poor explanation, right, for why these things are related. And of course, if you're going to ultimately create some policy based on this and decide whether or not to eat cheese, you really want to know whether it's causal, right? I like cheese a lot, so I like the example. Right, it's a big lifestyle change if it's not actually causal. Second, a more interesting type of explanation for me, especially for medicine, is why is this specific event happening? And so why is this particular patient unconscious? Why is this specific individual with diabetes having hypoglycemia? Right, all these sorts of things. And there, we're not trying to explain why two variables are related. We're trying to explain why a specific event is happening and why it's happening at a specific time. And there, having general information about correlations is not at all useful. Here, you need to know not just causal relationships that are true globally, but you need to know what's active at this specific time. So this is an example of, we created methods for doing automated explanation. The references in green were funded by NLM. So this was a tool for automated explanation where you can take a simulator, you have what happened in the actual world, so you follow a patient over time, and then you can come up with explanations for why it's happening. It's a really hard thing for humans to do. Here, this is an individual with diabetes. They go for a run. They might have a snack with the run, and then at some point later, they have lunch and they give themselves some insulin. But it'd be very hard for you to look at this, or if you're the patient with diabetes, to look at your glucose and then figure out, was it the run, was it the lunch, what's actually causing my hypoglycemia later? But using information about causality, we can actually say it was the two events together. Each one alone was insufficient. It was only the combination. And then because you know this is a causal relationship, you can learn for the future, well, if I go for a run, now I'm predisposed to being a little bit low, so I'll have a little bit less insulin with the lunch after. But if it's a correlation, you can't make this decision for the future, right? And then finally, control. All of these are about making decisions ultimately. We don't just want to learn about, it's interesting to learn about causal relationships. We know more about the world, but mostly we want to do something with it, right? And either prevent outcomes or produce outcomes of interest. And for controlling the world, causes are vital, and also knowing why the causes work. So one example is there was a randomized trial in Tennessee, and they reduced class sizes. Students had better outcomes and test scores. Other states like California looked at this and said, well, that's great, reduce class sizes, right, that'll lead to better outcomes. The problem is, in California, they reduced class sizes, but you need more rooms when you do that, and so the rooms came from other programs. If you reduce class sizes in a very large state, you need a lot more teachers. Not all of the teachers who are available were credentialed or experienced, and so lots of things changed, right? And then the intervention didn't work at all. So you need to know what actually makes the cause effective. Here, it's reducing class sizes while keeping everything else the same and having, high-quality teachers, having other programs and things like that. So you need quite a lot of causal information here to actually make a useful intervention. Okay, so if you've accepted that causes are actually useful, you might ask, why would we want to try to find causes from observational data? That's probably the hardest task we can try to do with observational data. And some people argue it's, one should just give up. In most of the cases that we're interested in, it's just not possible to experiment. I work on stroke using ICU data. It would be very hard to do randomized trials with stroke patients and then follow them during care. In many cases, I'll show an example of looking at risk factors before someone gets disease. It would be infeasible to wait 7 years to collect data to, predict what's going to happen before people become sick. And so it's really useful if we can go backwards and use retrospective data. And when I talk about medical data, I mean electronic health record data, which is a sort of traditional source of biomedical data, as well as intensive care unit data and patient-generated health data as well. So data from mobile devices, body-worn sensors, all these sorts of observational data, which provide different sorts of insight. So the cases I'm interested in are, can we use these to learn why things happen? And so some of the topics I've worked on are, can we learn risk factors for heart failure from electronic health record data? So they're using the EHR to figure out precursors to why people become ill. Similarly, why specific individuals have hyperglycemia using free living data from people with diabetes. And then in the ICU, trying to understand what's actually causing secondary brain injury based on observational data solely. I'll talk primarily about the challenges of these. So I won't talk as much about the details of the causal inference. But when I talk about causal inference in general, this is sort of the picture you should have in your head. I don't mean relationships between pairs of variables. I think in medicine, it's very rare that you have A causes B. If you imagine, A being smoking and B being lung cancer, it's really hard to take a set of data and decide who's a smoker and who's not. Smoking is sort of a continuous valued variable. You have different dosages. Someone could smoke for 10 years. Another person smokes for 20 years. These have different effects on your risk of lung cancer. And so it's much nicer to be able to treat these things as logical statements. And so you don't need to worry about the details, but this is just showing the types of things we can automatically learn. And so we can find, in a data-driven way, vigorous exercise causes hyperglycemia in a time window of about 15 to 40 minutes. And so there's also a time window for all of these things, because it's also quite important to know when an event is going to happen if you're going to try to do something about it in ICU or in outpatient care or in any other setting, right? You don't just want to know if you're going to get lung cancer. You really want to know, is it going to happen in 2 years or is it going to happen in 20 years? And you make very different decisions about your health depending on those. So we're able to identify these kinds of things. We can find the time windows in a data-driven way, but I won't talk about the details of that. And then there are a couple books on that. Primarily, I want to talk about what's different about medical data and what are some of the challenges specifically of large medical data. So the first is, it's really hard to determine what a diagnosis is. For example, I'll mention a case about heart failure. Figuring out which patients have heart failure was a sort of 2-year project at Columbia using the data there. You can't just use the ICD-9 code, and what's in the diagnosis or in a medical record is not the same as what's actually true about the patient, right? You have observations of the medical process, which are a different thing than the physiology, which ends up being quite important to remember. So we're measuring something that's different than the actual status, and so it can be hard to interpret results. And the second is the patients are changing over time, particularly in the ICU. They're quite non-stationary. One would hope they're recovering, but things happen over time. There are interventions, there are surgeries, other things are happening. Something is documented, and you don't really know when it's actually happening or when it's necessarily true, right? And so diagnosis, there's a time associated with it, but it started, at some point before it became clinically apparent. We don't really know when the onset time is. So it's one of the reasons also that we have time windows in the causal inference, because even if there's an exact time when something happens, we're definitely not going to measure things at exact times. And then finally, we have huge problems with missing data. We have lots of medical data, and then a lot of it is not there. And especially different things are measured for different patients, and we have to be robust to that. I'll talk about that in a lot of detail. Problems I won't talk about that we've partially addressed that are all quite important. Latent variables is an ongoing and persistent problem. How do you do causal inference when you might have confounding? Same thing, non-stationary data. We've developed methods for finding change points in time series data. Efficiency is a huge problem when you have vast amounts of data, so we develop more efficient methods for causal inference. And then Valerie mentioned a little bit about replicability. So we've worked on methods for simulation of medical data for actually validating algorithms, but I won't talk about that. So the first application I wanted to highlight was learning from EHR data. And so this was the first NLM-funded project a long time ago in collaboration with Columbia and Geisinger. And the challenges we had, if you're interested in causal inference and your outcome is heart failure, the first question is which patients are cases and which patients are controls. And then that ends up being quite a difficult challenge. You don't have perfect partitioning into cases and controls. And then if you have uncertainty in that, that affects all causal inference after that. And the second question is, if you're interested in causal inference with time series data, you need to assign a time to the diagnosis. But of course, our time is when the heart failure is clinically apparent and diagnosed, not when it actually happens. And that affects how you interpret results. So what we ended up finding was a sort of success story with about 30,000 patients from Geisinger. We replicated the results also at Columbia, which I won't get into. But here we found risk factors for heart failure and when they were happening before diagnosis. So diagnosis of hypothyroidism, diabetes, being overweight, these are all sort of known things, which was exciting. But then you find weird things like antihypertensive combination medication. It turns out blood pressure is very noisy, and so you don't find blood pressure as a cause. You find something that's a much more robust indicator of hypertension, which is being on medication for your blood pressure. And then the part where interpretation becomes important is we found diagnosis of urinary symptoms, which, if you know about heart failure, this is a symptom of heart failure. And so you have to remember that our effect here isn't heart failure itself, it's the diagnosis of heart failure. And so we were finding that the symptoms are happening actually before the diagnosis happened, and the diagnosis has a bit of a delay, right? So the causal relationships are always, of the diagnosis, not the actual disease, and there's no way to really get around that. But we were enthusiastic that we could learn something from EHR data. We could make use of, this was about 7 years of data for each patient. However, for acute illness, that's great, but for chronic illness, hospital data is episodic, and it's not really telling you what's happening at the important times. For a patient with diabetes, the doctor is not the person making the decisions about insulin dosing or meals or exercise. It's the patient themselves, and there the useful data is the data really outside the hospital in daily life when they're making these decisions. The challenge with that is data from outpatient settings brings many more challenges with uncertainty. The data is much noisier. There are also, outside of the hospital setting, many more things can go wrong. Devices break. In the study, one person went rock climbing, and then I think every sensor failed. And so you have challenges like that. And then the devices themselves are partially medical devices and then consumer devices and have a very high level of uncertainty, which isn't really accounted for in the causal inference methods. So there our challenge was, this was a relatively small data set. It was 17 people over 3 days. So how do you do causal inference where you can't really trust all the data points? Especially for glucose and diabetes, continuous glucose monitors have quite a high error rate. And so if you discretize data into episodes of hypo and hyperglycemia using very strict thresholds, then you're going to learn from the wrong data points, essentially. And so there we developed methods for probabilistic discretization and then assigning essentially weights to the data points. And so we could learn from episodes that are more trustworthy And then others, we don't throw away the data because it's still a small data set, but they get less weight in our causal inference. And there we actually found only if we did this weighting were we able to learn from the small data set. But once we did that, we were able to find things from this very noisy data set that previously had been found in very controlled settings in exercise physiology labs. And so we learned intense activity leads to hyperglycemia in about 5 to 30 minutes, and we found it with different sensors. This is a very well-known relationship. But again, it was only once we actually modeled the uncertainty in the data. If we didn't do that, then we found nothing interesting. And you just found if your glucose is high, it tends to stay high. So it's pretty important to understand the data generation process. But still, this was small data, outpatients. ICU is very exciting. Here you have people who are very intensively monitored. And so when I first started in ICU, I was sort of surprised the data on disk for about 50 patients here was the same size as 30,000 EHR data for 30,000 patients. And so these are quite intensively monitored patients. And you think, well, you have hundreds of thousands of measurements. Clearly, we can find causal models here. And the questions we're asking is, what's happening during recovery? What causes secondary brain injury? Which patients are going to regain consciousness? All those sorts of things. And so we had about 98 patients in this data set. These are patients that look like the one in the first picture I showed you. And so they have EEG, they have microdialysis, so brain metabolism. They have various other brain measurements, physiologic measurements, cardiovascular, respiratory measurements, things like that. Even though they're in the ICU and you don't have issues with lack of repeated visits and things like that, there's still an enormous amount of missing data. Devices fail, things are disconnected because someone has a surgery. Different things are measured for different patients, and then that becomes really important for causal inference because whether something is measured or not is extremely informative. Things are measured for a reason because someone thinks that, because of the patient's state or insurance status or things like that. And so if you just ignore the missingness, then you have a huge confounding problem. Things record at different frequencies, all sorts of fun stuff like that happens. And so this is just showing of the amount of data theoretically we could have, how much we actually have for the different variables, which nothing is 100%. Most are like 50%. Some are much lower than that. So it's quite a challenge, right? You have, in theory, all this data, but then you have lots of holes in the data. And so the first challenge we had of using this for causal inference was solving the missing data problem. Before we could do anything else with it, you have to deal with this. The other thing is, in the medical data, there are methods for imputation. In the medical data, you have multiple missingness modes. Whether a variable is missing or a measurement is missing depends on the value of the variable itself, as well as other variables. So we'd introduced new methods for handling that. So part of it is based on lagged correlations based on other variables. And the thing that's nice about incorporating lags is then if every measurement is missing for one time point, you can still impute a value for it. Whereas if you're relying on all the values at that time point, then you can't do anything if everything is missing. And often you do have the case where everything is missing. And then we combine it with the imputation based on the Fourier transform, and we made the code available. So after we solved that, then we could go back and do causal inference. This is one model showing brain-related variables. The other challenge is different things are measured for different people, and so you see two different numbers here. One is how many people we find that relationship in, and then the percentage shows you what percentage of people who have that measured that's representing. And so some things are measured in very few people. For example, RCBF is blood flow in the brain. It's measured in 14 people out of 98. And so we find this autocorrelation in half those people. And so it's giving some context. So we split the data into two different time periods that were thought to be clinically significant. And we actually found different causal relationships, which was interesting. It seemed that the causes of brain swelling actually changed over time, which then suggests maybe how you treat brain swelling needs to change over time. But again, the time period here was clinicians thought that this was an important transition at 96 hours. We don't know that this is the same for all patients. We don't know what's actually causing the change in relationships. We noticed in general there are more causal relationships in the later time period versus the early one, which might suggest things are being repaired. When things are going well, there are more causal relationships in biological systems because everything tends to be related to everything else. And so it might be a sign of healing, but we don't really know that. Yeah, and so one hypothesis was that's related to consciousness, which is another extremely important thing for doctors to understand. However, the data on that is extremely sparse, and it's also very time-consuming to assess. And so my collaborator, Jan, had found EEG can help you assess consciousness, that actually there were relationships between the changes in consciousness and patient outcomes, and that lesions were associated with impaired consciousness. The challenge is the instrument for assessing consciousness looks like that. And so doctors, they'll clap, and if the patient has a response to that, that's, one item on the scale. Can you follow someone's fingers with your eyes? Do you respond to commands? Can you feel pain? And so this is done basically once per day per patient. And so you have an extremely sparse time series during someone's ICU stay, and it's really hard to understand what's happening in between these two time points, these two or more time points. You have no idea in between those, and then two doctors can come to a different determination of consciousness, right? Because it's not objective, and it's also really time-consuming to do this. And this is just an example of part of it, right? It shows you just how detailed, eye movements and limb movements, going through this every time you want to know what the state of consciousness is. And so the project we've been working on is, well, what if we could automatically assess consciousness, right? If we could do that, then first you could improve treatment because you would know how aggressive to be about a patient's treatment. It would reduce the time burden on doctors. It would be objective, which would be really nice. It would be more frequent than once per day. And so all of our results were hinting at consciousness might be a cause of other things, but if you only know someone's state of consciousness once a day, you can't really understand causality because things are changing frequently and many more times than once a day, right? You have 2 points, and then in between anything could be happening, and we know for sure that there are fluctuations of consciousness. And our vision is ultimately you could have a dashboard in the ICU that shows you, all of your patients' level of consciousness over time. That's what we're working towards. So as part of that, we went back to what we found with the causal model, which is there were these interesting differences in time lags. And so I didn't show in the smaller figure, but all those relationships have time lags, and as well, there are different relationships across the time series. And it seemed like the timing of relationships was an important factor. And so we went back to, is that a question? No? Okay. We went back to the variables that seem to be important in the causal model, which are these respiratory and cardiovascular signals, as well as the brain measurements, and introduced new methods for finding when the lags between correlations change over time. And so when things are more synchronized versus maybe when things become out of sync and there's a longer delay between the variables. And so it ends up being a sort of hard problem to do this, but I won't talk about the details here. So this was about 61 subarachnoid hemorrhage patients in the neuro ICU. With a number of assessments of consciousness, but again, it's sort of once per day. It's not the same time of day for every person, and the number of measurements varies a huge amount per patient. For the moment, we focused only on impaired versus intact consciousness. So we have 2 states of consciousness that we're trying to understand, and we haven't focused on the sort of more difficult cases in the middle. What was really interesting was we learned that basically for all of these pairs of variables, for patients who had intact, so that's high levels of consciousness, the delay was much shorter compared to patients that had impaired consciousness. In impaired consciousness, no matter which pair of variables it was, there was a much longer delay in the correlation between them. And this was a totally different method than what we'd used to build the causal models, but we still found the same variables were important, and that we also found the same relationships between the variables. And so previously we'd found relationships between, for example, brain temperature and respiration, and brain oxygenation and brain pressure. And again, those come up as important. But now we're learning much more about what are the timing of these relationships and how they relate to consciousness. So the next step for this is using this for classification continuously in the ICU for assessing consciousness. Oh, and this is just showing the actual numerical lags. So you can see they vary. For some things, they're synchronized at less than a second. For example, brain temperature and respiration. They have a feedback loop in the patients that have high levels of consciousness, whereas in patients with low levels of consciousness, there's about a 5-second delay between them. which again intuitively makes some sense that, if processes are impaired, the feedback is going through other pathways or might be delayed somehow. So this was super exciting for me. When we go back, though, to the causal model, it looks like this. This is the entire causal model. I showed you prettier pictures that focused on brain and other things. I was excited by this. It was 5 years of effort. And then I showed it to Jan, and he said it's an unholy mess. So that was sort of dispiriting. And then we thought, okay, we have to work with the doctors and what they know, and how can we make this more understandable. And so the first thought was, well, maybe not everything is a cause here. Maybe it's possible some things are causes and other things are moderators of other relationships, and maybe not everything, can be intervened upon. And so if we can just separate out the stuff that's like a control knob from the things that are like switches, then it'll be simpler. And so we did that. Did not become simpler. We found more things. They were interesting things, but the goal of reducing complexity completely failed there. And so here we find, we can learn that heart rate, for example, or temperature actually also moderates the relationship between brain swelling, which is BRK here, and TW% is brain swelling. That moderates that effect on brain oxygenation, or the effect of brain oxygenation on brain swelling, sorry. But yeah, we didn't reduce the number of things, it just added more things and became even harder to make sense of, which was sort of unfortunate. And then this is the whole diagram, which again is a human factors nightmare on par with the first diagram I showed you. And so then the overwhelming question is, the goal of all this work is we want to give useful information to doctors so they can figure out how to treat patients. We haven't evaluated that. We evaluated accuracy of the causal relationships. Did they make sense? All those sorts of things. And decision-making has been a downstream thing that hasn't really been a focus. Which over the last year, this has been what we've primarily been working on is, how do people make decisions with causal information, and how can we improve that? And it turns out decision-making is really different than what we've been testing. So when you find the causal model, we're focusing on variables like heart rate and respiration rate. In reality, you don't get to intervene on heart rate, or you don't get to intervene on brain oxygenation. You have a strategy for intervention that can maybe affect these things, but that's a different thing, and you're selecting among strategies that don't exactly map to the variables that you can turn on and off in the model and see what happens if you turn those on and off. Nothing shows you what happens if you give this medication versus that medication, right? Which is actually the kind of decision you're making. And so it's true in medicine as well as in daily life. If we find information about factors that affect glucose in people with diabetes, you're not deciding about number of carbohydrates or amount of sugar. You're saying, should I have oatmeal or a fruit salad, right? And that's a much harder decision, and involves mapping what you already know, the causal model, to the choices that you actually have, which might be have a very fuzzy map to what we've learned. And so the second part of what I want to talk about is, how do we actually go from knowledge to action? So the first part was from data to knowledge, and then this is the long gap from that to actually doing stuff. Computer science, our evaluations have looked primarily like this. And so we focus on accuracy, FDR, FNR, how long things take to run. That's great. We want our methods to be accurate. But there's no evaluation at this moment for utility. It doesn't tell us that we find the right causes. We've primarily focused on finding more of the causes, finding more detailed causes, that sort of thing, finding causes faster. But we don't really know which causes do we find, right? It might be more important to find stronger causes versus weaker causes. That's not captured in any evaluation. The same point, finding earlier causes. If you can learn a cause of heart failure or type 2 diabetes or something like that, that could be prevented 2 or 3 years out versus something that's going to cause an outcome in 2 weeks, then an earlier cause is a more useful one to intervene upon. And same thing, not everything is modifiable. So maybe we should prioritize what we can actually intervene upon and affect versus causes that we have absolutely no ability to intervene upon. And so family history or things like that, it's interesting, but it's not actually a modifiable factor. But currently everything is evaluated equally, right? Nothing is weighted in any way in importance in our evaluation of inference algorithms. And we don't really have a sense of what makes a cause useful, which causes are more useful than others, and do we know that we're finding the right ones? There's been a lot of work in psychology about learning causal information. So it's shown on the positive side that people actually can learn causes. People can make decisions with causes, but it's been primarily about very abstract settings. And so it's contains that it's focused, just on the information that they give the participants. And so they're not using outside information or anything like that. And so the examples are things like you have aliens that can read each other's minds, how is information transmitted, or which alien should I intervene on to make another one think something, or drugs and microorganisms, which seems sort of biological, but then they're very abstract drugs, or they're made-up drug names. They're not related to drugs that you know or have any experience with. Or the classic example is like blicket detectors. You have a box, and which blocks can be put on the box to make it go, or to make it, which blocks or blickets that make the box play music. It's a tongue twister. But none of these relate to daily life, right, in any way. And so we don't really know how do people combine causal information with their existing knowledge and how they make decisions with that information. And so the project we've been working on is, can causal information aid decision-making in familiar scenarios, and does it work differently in familiar scenarios versus ones that are more abstract and that people don't have familiarity with? So our first setting was, we've been doing studies on mechanical Turk. First study is with about 1,700 people on mechanical Turk making a decision about managing weight. And so here they have a question about an individual. She just started college. She doesn't want to gain weight. She's heard about the freshman 15. And she has competing desires. She wants to make new friends. She wants to have fun. She also wants to, do homework and study. And so she can't devote her whole life to managing her weight. And then you have a causal model that tells you about the relationship between social pressure, diet, exercise, and weight. And then the options for the participants are, what should this person do? Should she go for a walk every weekend, maintain a healthy diet, not hang out with her friends? Should she watch less TV? That sort of thing. And so unlike the prior work in psychology, this is much closer to what you have in daily life. And you'll notice that the answers map to the model, but not exactly in that case, right? You have to do a little bit of work to understand them. And so our hypothesis was, causal models will help people make decisions. They'll reinforce the connection between your action and the goal, and it'll be great. It was not great. So we learned on the positive side, first, people were actually really good at figuring out what to do to maintain their weight, at least in this setting. They might not be able to put it into practice, but in this controlled setting, they know what the right answer is. With no extra information, 89% of people got it right. When we gave them a causal model, 80% of people got it right. And so it seems a little bit concerning that, so I've devoted 10, 12 years at this point to causal inference, and then causes made things much worse. But this was a case, it was a familiar domain, and so it was essentially what's happening with my collaborator, Jan, who sees the causal model and thinks it's a mess and doesn't know what to do with it. Here, people are combining what we show them with their existing beliefs about diet and exercise and things like that. And you'll notice also there's not really a difference between text and diagram. It's not that people have problems with diagrams or that text is better or whatever. In both cases, causal information led to worse decisions and less accuracy. So the hypothesis was, maybe people are doing worse because they have domain experience, right? Maybe it's, challenging for people to map what they already know to this new information, and that's where it's going wrong. So we did a follow-up looking at decision-making in diabetes. It's a nice case because there's a large percentage of people who have experience in diabetes management with type 2 diabetes, but also a sufficient number of people who have never thought about making decisions to manage diabetes in their lives, and would treat it like a novel scenario. We also made the diagram simpler. The other one, maybe there are too many nodes, too many variables, it's hard. Here there are 3 nodes, and we have an individual who has type 2 diabetes, and tells them about, how do you manage diabetes, and this person his goal is to manage his diabetes without insulin. He wants to do it with diet and exercise, but here's what he does normally. So on Fridays, he usually meets his friend for hamburgers. Now he's not so sure, and he wants suggestions about how to keep his diabetes under control, and again, maintain his goal of avoiding insulin injections. And so here again, the choices don't map exactly to the figure. So the figure tells you about carbohydrates and exercise and blood sugar, which is what we would find as the output of AI and machine learning methods, but the actual choices are, should I walk to dinner? Should I order a sandwich? instead of a hamburger? Should I have a sandwich and go for a bike ride? Or just, give up and do the usual, right? And so it takes some work to map from the figure to the options. And so here the interesting thing was some people are helped with the causal information. For people who didn't have diabetes, when they were given the causal model, they did significantly better. They increased from about 71 to 87% accuracy. And so causes actually are useful. People with type 2 diabetes did worse. You'll notice there is a smaller percentage of people with type 2 diabetes, so the error bars are larger. But people with type 2 diabetes made worse decisions with the causal model, and it was closer to the case with the weight management, where people have experience, they see the model, they have conflict maybe between what they already know and the model we're giving them, and then accuracy plummets. So we were sort of heartened that non-experts were helped. It's still frustrating that people who know something are not helped. And so the question is, why is that? And so we followed up and looked at confidence to see, maybe people are second-guessing things and they're losing faith in what they know. They're having difficulty mapping this new information to what they already know. We compared that. And so we actually found that. So in people who have experience in a domain, this was decision-making about weight management again. 83% of participants with no extra information were very confident in their decisions after they made them. Of those, actually, the confidence was not misplaced. 92% got the answer right. So they were confident and they had reason to be confident. When we gave them the causal model, accuracy went down to 70%. And of that 70%, now only 82% got the answer right. And so accuracy was worse, and the people who were confident shouldn't have been quite so confident. But then when we compare it to people who have no experience, we see exactly the opposite. And so on making decisions about managing diabetes, most people did not have confidence in their answers, as you'd sort of expect for people who don't have experience in type 2 diabetes management. Here, only 42% were very confident in their answer. They actually did better than would be predicted by their confidence. But it's confidence, I think, relates very strongly to their experience, and they just didn't have experience in the domain. And on the other hand, we see with the causal model, they're much more confident and also much more accurate. And so it's exciting that for novices, causal information actually, people can use it. It improves their confidence in their decisions and their accuracy. But we need more work on how to actually make this useful for experts. So what we learned with that was first, action requires causality. We don't want to get rid of causes. If we want to make useful policies and interventions, we still need causal information, but it's not enough. We need causes plus something else and more tailored causal information. And so the sort of first takeaway is we need evaluations of not just accuracy of algorithms, but the utility of the algorithms to be sure that we're actually finding the right causes and introducing methods that prioritize the right causes or the most useful causes over just finding the largest number of causes. And that, it should be something that we prioritize when developing algorithms versus just, at the stage of clinical decision support. Does the output help people achieve their goals? Does it speed up decision-making? That sort of thing. Not just, are the causes right or wrong? And then assuming all causes are equally important. There's been, in AI machine learning, increasing understanding of the need for explainable AI methods, and so understanding how all these algorithms work, which features are important. But I would argue this is different from usable AI, because the explanations are still primarily for the researchers to understand how the algorithms are working, and they're not really usable by doctors and lay people who are not experts in the algorithms. So there's still an extra step we need to something that's actually usable by lay users. The second interesting thing was, if you look at the results on confidence, now what happens when you give these causal models or this new information to a doctor and patient for shared decision-making, right? People have totally different mental models. You're giving them the same information. Some confidence might be increased, some might be decreased. We clearly need personalized information and a better understanding of what people already know and then how to put new information in the context of what they already know. And so eliciting mental models from both doctor and patient and understanding where there might be conflict between this new information we have and their existing models, and potentially reconciling those in an automated way or figuring out how to tailor the information, as well as to the skill level and expertise. And the last one is capturing and modeling decision-making. So this is not new in the context of clinical decision support or fields like that. It is new in AI and machine learning, where we sort of assume we have data, we have an algorithm, we apply the algorithm to the data, and then our job is done. But we need to close the feedback loop and have information about how is the output actually used to make choices and influence care so that we can feed that back into the AI machine learning in the first place and understand what's the effect of the causes we're finding and how they actually impact the decision-making process to determine, utility of the models. But right now we don't really have data on that, which is an open gap. And then I just want to thank Jan at Columbia as the primary collaborator on stroke and all things, the ICU data. But this is also collaborative work with Stevens, Lehigh, and other researchers at Columbia. And it's been funded mainly by NLM at NIH, as well as some other funding from NSF and the McDonald Foundation. Thanks.
So we have lots of time for questions, I think. Yes, we do. Anybody have any?
I have a question.
Yeah.
One part you presented the no experience and the experience. It seems that the experience, with the experience, if you use a causal model, you get less correct. Does that mean, I have the problem is like how to judge the correctness of the causal model. Is that judged by the experience or, of course, you can do the test judged by the ground truth. So that's a very interesting observation. That means, to me, the causal model, in this case, that experience is not the correct experience, maybe.
Yeah, so we've done other studies separating out experience versus proficiency, right? Just because you have type 2 diabetes doesn't mean you're managing it well, right? And we found it was primarily perceived knowledge that was the thing that was driving it. And so people who actually, have knowledge that's correct did much better, which is good. So there were some positive results. But people who thought they knew a lot were the ones that had conflict with the new information and then had the reduction in accuracy, and maybe they were, less receptive to it. On the question of how we were judging accuracy here, for all the decisions, there's one option that dominates all the other ones. So there was one objectively correct choice that we could use for evaluating accuracy versus just preferences.
Another question is we have a lot of data to show the correlation without time, because the data, if we may not have a time series data, if we have like before and after data, it is possible to infer some causal relations. But sometimes we only have a snapshot at one time point. In that case, how to infer the causal relations between variables?
Yeah, so all of my work is on time series data. I love time series data. There exist methods, so Bayesian networks, there are methods for inferring Bayesian networks from static data. So there exist methods. In time series, many things are easier because you can orient relationships in that way. Other things are harder, so there are methods for handling latent variables and static data that don't exist or don't sufficiently exist for time series data.
Thank you.
Yeah.
So, I'm sorry. So my question was somewhat related to that. I read a paper recently from the AI group at Facebook, and the author claimed to be able to extract causal signals from static images for purposes of analyzing objects in the images. This is related somewhat, I think, to your answer about being able to analyze static data. Do you think, in your opinion, would this analysis extend? Is it feasible to extend this analysis to getting information about objects in static images through a causality analysis?
I don't think I understand what the causes are there. I'm confused. Do you have multiple images over time, like a video, or
No,
like what?
no,
what
no,
are
no,
the,
strictly static
cause?
images. So what the research consisted of was removing the objects and then computing features from the images with the objects removed, as opposed to having the objects in the images. And then, and I don't know the details of the causality computations, but they claim to use methods from causality theory to compute what they called anti-causal signals for the objects, and then showed how these anti-causal signals were consistently related to features in the images that were computed by conventional methods.
I haven't seen the paper. I'd have to take a look. For me, this is one case where maybe you don't need causes. There are lots of image processing methods that could do as well. Maybe causality can help. I definitely have nothing to contribute to image processing.
Thanks a lot. Appreciate it.
Sorry.
So I'm wondering about the role of causality, whether that's really what's important in some of these things, and whether you really demonstrate it. So, like you gave the example where whether somebody had been put on blood pressure medication was a better indicator than their blood pressure, but presumably being put on the blood pressure medication was not causing the congestive heart failure. And I'm wondering about like consciousness. Are you confident that you've demonstrated that that's causal, in that an intervention that would maintain consciousness would be likely to be effective, or are you seeing something akin to Granger causality, which I think everybody agrees doesn't imply actual causality?
So, sadly, not everyone agrees that. There are a lot of papers arguing Granger causality is causality. I disagree vehemently with that. But so I think absolutely it's important that we have causal relationships if you're going to base treatment decisions based on what we find. Many of the treatments have significant risk, and so if you're just treating a symptom and not something that actually can prevent bad outcomes, then that's quite important. Do I think that we've demonstrated causality? I think it's never possible in the really difficult observational data we have. It's never going to be you take ICU data or EHR data, you apply some inference method, you find causes, and that's the end of the story. The extent to which we believe they're causal is the extent to which we believe various assumptions are satisfied about confounding and stationarity and things like that. And I think what you can find from the ICU data is you can generate hypotheses, and then, at least in the case of stroke, that maybe need to be validated in animals afterwards, and that's a long process. But it's not like the end of it, it's the beginning of it, and what you find. Does that answer your question? Okay.
So you made that comment. I'm a human-computer interaction person, so naturally my questions are, so the experts and the people who weren't expert at different scores, and do you desire, I guess, to try and dig into the why? I'm just curious whether part of your research plan in the future would be working with the people as opposed to only the data. Not that you are only the
Absolutely, yeah. So we've been doing large tests on Mechanical Turk because there you can have very large sample size, and especially for something that might have a heterogeneous effect or might be differently different people. That was a good first step. And so there we've been looking at the effect of, like I mentioned, actual expertise versus what you perceive your expertise to be. And it turned out the perceived expertise was what was driving things. I think the next step is trying to understand the decision-making process and then have studies in the lab where you can follow what are people thinking when they're doing this, how do they interpret the information. But it's also a challenge that people aren't very good at describing how they make decisions and what they're thinking.
So that's been true for decades.
Yeah, and so it's not clear that.
Decision makers to unpack those.
Yeah, and so we have found that if you reveal to people how little they know beforehand, and so there are exercises in psychology, there's the illusion of explanatory depth, and then we start to write out a causal model, you realize basically how little you understand the connection and things like how a zipper works or how a toilet works. And so people did that first, and then they realized, hey, maybe I don't know as much about this topic as I thought. We thought they'd be more receptive to a new causal model. It didn't completely remove the effect, but it helped a little bit. And so part of it is, having an accurate assessment of what you know might be important first. And so I think we're hopeful that there'll be ways to actually improve the decision-making process, not just find, here's how it goes wrong, but what we can do about it.
I have another question. Can I ask? Oh, you can go ahead.
Both the examples that you gave to the Mechanical Turk participants are examples where, in practice, people are trying to deal with multiple competing goals. They want to eat. They want to have fun with their friends, and they also want to not gain 15 pounds. And the causal model only dealt with okay, yes, these are the things that will help me not gain 15 pounds. But when I was looking at the question, I was tempted to say, well, what should I do if I also want to make sure that I have as much fun as possible with my friends? So it seemed to me that that's a confounding factor in the decision-making process.
Yeah, so I think there are two answers to that. One, we've also done studies where there were no competing goals and people did just as badly on the decision-making question. But now what we've been working on is personalizing the causal models to the individual. And so exactly for that reason, you might have different priorities than someone else. And so ultimately we should show you different parts of the causal model that would show you, how do you maintain, fun, as well as diet and things like that, whereas maybe someone else has a different focus or has different time constraints, and then we would show them different parts of the model than we would show you. And so it goes back to the personalization.
Can you comment about the usable AI, like AlphaZero Go, and also other techniques from the deep learning? If the usable AI is so advanced, what is the point to do the explainable AI? I know from the knowledge point of view, explainable AI is human, of course, want to have that. But like AlphaZero, I think, what do you think it is belong to the usable AI? We cannot explain. Or people to some extent can explain, but may not add to the knowledge of the human knowledge.
Yeah, I think I understand your question. For me, I'm interested in the cases where the algorithm or the computer is never going to make the final decision, where it's always going to be collaborative with a human and an algorithm. And that's the case where you need to somehow, work with the human and understand what they know and how to fit in that context. Whereas the explainable AI I see as more a tool for researchers, right, to understand how the algorithms work, how you can improve them. Are you overfitting to? There was a case in computer vision distinguishing, I think, dogs from wolves, and it was overfitting to the background. And so if it was snow, you know that it's probably something that lives outdoors. If it's inside, it's a dog. And so there you can understand, the algorithm is focusing on the wrong things, but that's not really usable by someone who wants to use the algorithm for a specific purpose, right? There it's, how do you make choices based on it, not necessarily how does it work, which is, I think, a different thing. And so my focus is, how do you use it for a purpose versus, I don't think the doctor necessarily needs to know, all the details of what features are important, and all the, things that a researcher would want. They want to know what information is it relying on, how does it relate to the patient, what's modifiable, what intervention options do I have, and what would be the predicted effect of those intervention options, which is, I think, a different goal.
I'm still thinking about that picture of that poor guy with 1,000 little screens around. and really, so because you made the comment about the record, the electronic health record being a record of the process, not of the patient. do you think that that sort of setup is providing that other side? I mean, I'm actually curious. Who uses, do different people use those data streams to make decisions? Do they come together?
I think that's a mix, and then, I mean, some things are continuously recorded, others are literally like written down by a human approximately every hour, maybe every hour and a half, it varies, and it's, you know, or some things are documented when they're important, and then you have the sort of meta process of it's written down, and so that's giving me other information that the person who saw this thought it was an important measurement that meant something. And so that's what I mean about like the data being there is informative about the process and what was happening. But none of it, even the stuff in the ICU, it's still not someone's actual physiology. It's a noisy measurement of the physiology, right? You never have the actual brain activity or heart rate or, you know, brain swelling. We have a variable that we think is a proxy for brain swelling and tells us something about it, but it's never the actual thing, which you can't measure, which it's fine, but it's just important to keep in mind when you're interpreting results, and especially doing causal inference, that, you know, the effect and the cause are proxies for, you know, what you actually care about, and they're never the real thing.
So a delayed follow-up to my earlier question, and I've thought about it some more. Could you just clarify, like with respect to consciousness, are you showing something stronger than Granger causality? And, you know, more generally, I mean, are you really making the case, because this is a hard thing, that you've identified it as being actually causal, that it's likely, you know, and I understand if it's the best you can do,
but,
the best you can, it's not a criticism, I want to understand to what extent we can really infer causality from this sort of data.
So on the
other than a formal sense, right?
In the consciousness, we haven't shown anything causal. So we had causal models with the physiology data, so we had causal models about brain swelling and things like that. For consciousness, all we've shown are factors that we can use to understand your current state of consciousness. And so there it was, we found these delays are related to consciousness. Those definitely are not, at this stage, causal. And I don't think that they would be causes. I don't think the delays in, I would think it's more likely that the lagged correlations are effects of your state of consciousness, that they're not actually causing your state of consciousness. But there, our goal at the moment is developing something that you can use to continuously, a continuous value that's a proxy for consciousness. And then using that, the hope is that we can find causes and effects of consciousness, potentially. But we haven't done anything causal with consciousness.
In the cases you're calling causal, have you shown something stronger than Granger causality, or is that what you mean by causality, I guess, just to clarify?
Yeah, I believe we have. I mean,
briefly, what is that? Could you, okay.
I'm going to suggest, come up here and talk to her about it. We've hit our time zone, so we have to say thank you to you, but I'm sure that you can continue the conversation.
I'd be happy to talk more in detail.
And I want to thank you very much.
Thanks.